Hey everyone, welcome back, and today let's solve Leetcode problem 1358, titled Number of Substrings Containing All Three Characters. So we're given a string S consisting only of characters A, B, and C, and we want to return the number of substrings that contain at least one occurrence of each of those characters, A, B, and C, meaning we want all the substrings that contain all of those characters A, B, C's, where the frequencies of all of them should be at least 1. So in example 1, we have our input string S to be A, B, C, A, B, and very simply we have an output of 10 because, of course, we have 10 substrings that have at least a frequency of 1 for all three of these characters, A, B, and C. And to kind of list out all of those different substrings of the input string S that have that property, they would be A, B, C, and the following, right? Now, as you can see, we have ABC 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. ABC is actually repeated, but very importantly, they are from different indices. The first ABC substring that contains all of these values with a frequency of at least 1 comes from indices 0 to 2, and the second occurrence of the ABC substring that again has that property comes from indices 3 to 5. That's very important to note, as even though we have repeated substrings that still have the property, as long as they are from different index elements, at least differing by at least one element, they still are counted as different substrings, which is also important to note for the context of this problem and the solution implementation. In example 2, we have our input string S to be AAACB, and in this case, we actually only have 3 characters or substrings that contain all of these characters. It would be AACB, it would be AACB, and it would be ACB, right? In example 3, and of course any other substring that we choose, like just AA or AAA, it wouldn't contain every single character AC and B at least once. In example 3, we have our input string S to be ABC. Now, we can only form one valid substring, and that is the entire substring itself, because it has a frequency of exactly once for each of the characters A, B, and C, and so that is the only possible substring that we can form, and so we only have an output of 1. So for the constraints, here we see that they're guaranteed that, okay, we have at least 3 elements that are input string S for all examples, so we don't have any invalid inputs, and it's going to be at least 5 times 10 to the 4th power, which is a pretty large value, especially in relative or typically for constraints and input sizes. And we're also finally guaranteed that S is only going to consist of A, B, or C characters, no other invalid or unnecessarily extra characters or elements to worry about, even further simplifying our solution and logic for this problem, which brings us to the main observation that we can really make. This is very similar to, I believe, Leetcode problem 209, subarray minimum summer, something like that along the name of what it's called, right? It has a very similar logic, right? Basically, that kind of leads us to the main observation that we really need to make, is that whenever we actually find a valid substring as we actually iterate through the input, every single suffix of that substring also has to be valid, right? So that brings us to the main kind of technique or algorithm structure that we're going to really follow to solve this problem, right? Since we are actually dealing with these substrings and checking these kind of conditions very efficiently, the best approach to actually solve this problem is actually something called the sliding window algorithm. And to kind of put this into context, put the suffix idea into context, where we say whenever we actually find a valid substring, all of its suffixes would also be valid if, per se, A, B, C, and I'll just comment this out as a sentence. I think it's most simply easily to understand. If this exists, as we saw in the first example, I believe it was, at indices 0, 1, and 2, meaning A is at index 0, B is at index 1, and C is at index 2, we also know that if we extend it to 0, 1, 3 or 0, 1, 4, it still would be valid, right? That's kind of the suffix property or idea of this solution. If we have ABC, well then shouldn't ABCA also work? Yeah. Shouldn't ABCAB also work? Of course. Shouldn't ABCABC also work? Yes, it should. We're not removing any important characters. We're just we're just constantly adding on to them to make those suffixes still count as valid substrings in addition to this ABC. And so kind of like the reverse logic, if we had ABCAB, even if we remove this A, we'd still have a valid substring like this. Even if we remove this B, we'd still have a valid substring like this, and we can keep checking that while we still have a valid substring substring until once we remove this A, we wouldn't have a valid substring anymore. That's the main sliding window logic or algorithm structure that we really need to keep in mind for the problem. Right, and that brings us to the actual explanation of how we're actually going to solve it. We'll use 2 pointers, a left pointer and a right pointer, to actually dynamically adjust our window while actually checking for when our window is valid, meaning it contains a frequency of at least 1 for all characters A, B, and C as we iterate through the input, where right would simply expand to include more characters in our for loop, and the left would actually shrink our window when we actually have a valid substring and we're trying to count all the possible substrings while removing elements from the left end, or the left end of the left pointer. Right? So effectively, on a high-level rundown, we're going to have a dictionary or an array to actually keep track of the character counts inside the window dynamically that we actually adjust or update. And we're also going to have that 2-pointer sliding window approach. That's actually going to be used to expand and also contract or decrease the size of the window dynamically, and also a variable to actually count the number of valid substrings when we actually find one. And of course, we would actually have that as our result or output. Right? So let's go ahead and get into the solution here. Okay? And again, just kind of bear it in your heads. Expand the window by moving the right pointer. All right, and we also do this by updating our character count. We shrink the window from the left side or from the left pointer when we have all 3 characters with a frequency of at least 1. And then we start to count all the valid substrings that we actually form from the current window position to get the number of total substrings that have that valid property. Again, kind of extending off on that suffix idea. All right? So like we just talked about, let's first initialize our count hash map or dictionary, if you will, in Python. And of course, before we actually find anything, the counts or frequencies of all of these characters would be initialized to 0, because of course we haven't actually started iterating through the input yet and forming any substrings. But this dictionary count is going to keep track of the number of times, or how many times we've seen A, B, and C appear in our sliding window that we adjust dynamically, again, as we iterate through the input, right? So of course they're all initialized to frequencies or occurrences of 0, because of course we haven't seen them yet, as we haven't started iterating through and forming any valid substrings yet. And of course now let's actually get our left and right pointers here. So left is going to be initialized to 0. This is what we actually represent the start of our sliding window with, and this is what we use to contract the window size. And the right pointer we're actually going to use as our iterator that we actually expand with a for loop, right? So let's actually get the results as well. And like we were talking about, this is our output. This is actually the number of, or total number or count of valid substrings that we find and that we increment as we actually iterate through the input and find all the valid windows, right? So now let's actually get the right pointer and start iterating through the entire string. So for R, or I'll say right to kind of symbolize that right pointer, in the range of the length of our input string S, right? Again, this is a very simple implementation of this sliding window algorithm. We're actually moving the right pointer through the entire string, using it as our iterator in the for loop. This is basically simulating expanding the window. And for each iteration, we want to get the count, and we want to increment the current value at that index right frequency by 1, because of course we've seen, or this current character, A, B, or C, whatever it is, and we're adding the character to our current window. And so, of course, we also have to increment its count of that specific character as that index right in the count dictionary, right? So once we actually get that, now, while all of this is true, kind of a shortcut in Python, but I'll explain how the syntax works. So while all of this is true, so while count at C, while it's greater than 0 for all C in all characters A, B, C. While that's the case, we want to actually increment to our result the number of actual valid substrings that we can form. This would be the length of S minus right. This is the main logic of this solution. Here in this main while loop for the sliding window algorithm, to actually check while we can actually contract our current window, effectively here we're checking if all the 3 characters are actually present in the window, and while all of this is true, meaning for all C's or A, B, and C in the count hash map, while all of them have a frequency greater than 0, or in other words, at least 1, we can keep applying these operations, right? If count at if count at A is greater than 0, count at B is greater than 0, and count at C is greater than 0, we still have a valid substring, and we can continue to decrease the size of our current window and increment our result for the total number of substrings that have that property accordingly. And this is the main observation that we really need to make from this problem here. We're adding to our result the total length of our input string S minus wherever our current right pointer or rightmost value is of our current window. Right? Effectively, to kind of put this into more formal terms, if we actually find a valid substring that ends at the right index, then every single substring that starts from left to, right? And extending to the end also has to be valid, that suffix idea. And so we have to add the length of s minus right to the result as well, because all of those values that we can potentially extend, those suffixes would still be valid, like we saw in ABC. If ABC is valid, then ABCA is also valid, ABCAB is also valid, and ABCABC is also valid. We're adding on the total length minus the pointer. The right pointer, right? Because the right pointer is going to tell us how many values that we've covered so far in the current window, and these rest values, the rest of the values here, the length of s minus the rightmost value, that's going to give us the number of characters that we can still add to our current valid window as suffix characters to extend or kind of contribute to the suffix of the current window to still make sure that our window is still valid, right? That's the main suffix idea. Now, once we've actually incremented and updated our result accordingly for the total number of suffixes and still valid substrings that we can add to our current window, now let's actually start to contract or shrink the window with our left pointer. So first, let's get count at s at index left, whatever that value left is in this current iteration. Let's decrease it by 1. Why are we decreasing it by 1? Because now we're excluding or removing the leftmost value from our count hash map, decreasing its frequency by 1, and now moving to the right, moving the left pointer to the right one, basically just incrementing its value, the left pointer's value that is, by 1, right? We're basically trying to find the next valid substring by moving 1 to the right. And here on line 11, we're basically shrinking the window by moving the left pointer forward and decreasing the count of the value at that left index previously by 1. And effectively, we're going to continue to do these operations and continue to shrink the window and move our left pointer right while we still have all the characters in ABC, basically all A, B, and C with a frequency of at least 1, meaning we still have a valid substring. We're going to keep doing this. And effectively, once this for loop is done executing, once we've checked all the rightmost characters, basically every single character as a rightmost possibility character for all valid windows, we're simply going to return our result, building off on that suffix idea. Of course, the result would actually hold the total count or number of valid substrings in our input. So unless I made any syntax errors here, there should be accepted and there should be a valid solution. And as you can see, this really is just about as efficient as you can get it to be. So on a high-level rundown, how does our solution work? Again, basically, we're very efficiently counting all of the valid substrings using this two-pointer sliding window technique. Effectively, we're expanding the window by moving right and also tracking our character frequencies accordingly. And when we have at least one A, at least one B, and at least one C in the current window or the current substring, we're counting all of the valid substrings starting from left, building off on that suffix idea of the number of characters that we can still continue to add to our current window and ensure that there's still suffixes of the current window and our current window would still be valid with those characters. And then we shrink the window from the left and basically just shrinking its length and continue to do that searching. And we're going to kind of repeat this process in this while loop here for all values in our input until we reach the end of the string. So for the runtime complexity here, it is actually going to be a big O of n or linear time solution. Why? Because really this is just a one-pass solution. We have a singular for loop here. And actually, each character is processed not once, although we do have a singular for loop here. We actually do have this while loop here checking and shrinking windows as well. So each character is actually processed at most twice, right? Once when we actually expand the right pointer in this singular for loop here, and at most once when we actually move the left pointer forward accordingly. And since we iterate big O of n for right and big O of n for left, the overall fully simplified runtime complexity would be linear in big O of n, and that brings us to the memory or space complexity. That's actually going to be constant or big O of 1. You may be thinking, wait, we have a count hash map here. That is the auxiliary memory or the singular extra data structure that we're using. Why is it a constant memory? Well, we're only guaranteed to be storing at most 3 characters in our dictionary, right? We're always guaranteed that we only have 3 keys in our hash map. And so we're guaranteed that since that's constant, it's going to be a big O of 1 or constant space. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.